So now that we know how to identify a Poisson distribution, we can use this formula here to calculate Poisson probabilities. For example, what's the probability of a certain number of fish passing through a channel in a given time frame? So to do that, we need to know three things. First, the number of successes that we're looking to have occur, right? This is the same parameter, the same concept that we had when we were talking about binomial distributions. Second, we need to know the average number of successes in a given time interval. For example, how many fish swim through the channel on average per hour, or how many cars go through a drive-through per minute. And we're going to represent that using this Greek letter lambda. And finally, we need to know the time that we're interested in. Now, the lambda parameter is the only one that's going to be constant based on the physical circumstances. X and t are both values that we'll get to choose. For example, we might want to know what's the probability of 5 fish swimming through a channel in 30 minutes. Right? Now, the one thing you have to watch out for is the units on the two time parts here. The time unit on the average rate and the time value that we're interested in, the value of t, are both going to have the same units. All right, so I've got an example where we're back to the salmon run that I talked about in the last lecture. And now I've narrowed this to a specific question, right? I want to know what's the probability that 7 fish pass through the checkpoint in 2 hours. All right, so let's look at our three variables. We're going to look at x, we're going to look at lambda, and we're going to look at t. X is the number of successes. So a success here is a fish swims past our checkpoint, right? And we're looking for the probability that 7 fish do that. Now the constant rate, that is 5 per hour, and I like to throw units in here. As a matter of fact, we could add fish up here, right? And we can make this 5 fish per hour. I know, remember, I was just saying on the last slide, we have the potential for a unit conflict between between lambda and t. So I found that putting the units in there really helps you to focus on that, so it's easier to notice if there's a discrepancy. Now, t is the time frame that we're interested in. Well, the question specified 2 hours. So t is going to be 2 hours, and the units match, right? So we're in good shape. We don't have to worry about that. Now it just comes down to use the formula, right? I'm looking for p of 7, that's our x value, equals, let's see, lambda t, that's 2 times 5 to the x power, that's 7, divided by 7 factorial, e to the negative 5 times 2. And now it's a calculator exercise. Where you go to your calculator, and remember, you always want to be careful with your calculator. For example, it wouldn't hurt to throw parentheses here to make sure your calculator knows that 2 is up in the exponent. All right, but when you do this, you do your data entry, this should come out to 0.0901. About a 9% chance, right, that we will see that many fish come through in a 2-hour period. Fairly low, right? But that kind of makes sense, right? If we expect to see 5 per hour, then over a 2-hour period, well, 5 fish per hour times 2 hours, that's 10. So we're kind of looking for something to be a little closer to 10. So yeah, I'm okay with 7 being a relatively low number. All right, so take a look at this one. You can try this out yourself if you like. Go ahead and pause, right? Then come back and we'll work through this together. All right, so we're looking to do the same thing, but we have an at least probability here, right? I'm looking for p of x at least 1. That would be greater than or equal to 1. And our Poisson formula is a lot like our binomial formula. It only handles equals. All right, but remember, I'm going to use our complement rule. The complement of x greater than equal to 1 is the probability x equals 0. And our complement rule says the sum of those have to be 1. All right, so x equals 0 I should be able to do, right? Let's look at our parameters. I'm looking for 0 hurricanes, and I need lambda and t. T is going to be 1 because we're talking about a given year, a single year. Okay, so how about lambda? Well, we weren't given that, right? But look, I have number of hurricanes and a time frame, right? The number of hurricanes was 31, and the number of years. Be careful here. People are you're always tempted to subtract, right? 2014 minus 1900 is 114. It's not 114. It's 115. Remember, when you subtract, it doesn't count that first number, right? For example, let's do a real quick, simple example. Let's say I wanted to do between 2001 and 2003. If I just subtracted, I would have gotten 2. But this is actually 3 years, right? It's 2001, 2002, and 2003. So you have to kind of manually add that first year in. Right? That's why this should come out to 115 years. All right, which is 0.270. All right, now I'm going to go to my formula. Right? This is 0.270 times 1 to the 0 power divided by 0 factorial e to the negative 0.270 times 1. And this actually comes out nice. Anything to the 0 power is 1. 0 factorial is 1. So that whole first big expression there just kind of disappeared. And all we're left with is the e part. Right? So that comes out to, according to my calculator, 0.763 equals 1, and we'll bring down this probability. So to get the probability, I'm just going to subtract, right? Move that over to the other side. The probability of getting at least 1 hurricane in a given year is 1 minus 0.763, which is 0.237, 24%, almost 25, right? So moderately likely, right? Moderately likely to happen. Okay, so what's next? Now that we can identify a Poisson scenario and calculate probabilities for it, the last thing we need is a way to determine the mean and standard deviation of a distribution, of a Poisson distribution, so we can talk about, among other things, when a value is unusual and when it isn't.